So we've been basically building up to this point for the whole lecture series. So we've talked about how we produce Higgs bosons, how we detect particles from the decays of Higgs boson. Now we're going to talk about how we take that data and really decide that yes, we've seen a Higgs boson or not. So this is finding that proverbial needle in the haystack. This is just what we've gone over, so there's no lectures for 2 weeks, and then on the 14th we're just going to talk about what's next for the LHC. So we've been shut down for about a year now, and then what are we going to do next? All right, so as usual, we're going to start with a review from last week. So last week we learned about the data volume that the LHC produces. So the LHC produces 50 terabytes of data per second, and we said that that's 1 megabyte per event, and a 500-page book, like the God particle, is 1 megabyte, so that was our comparison. But that we only store about 54 terabytes per day. That was the data reduction volume going from what's produced to what we store. And the way we decide which of these 50 terabytes per second to save is that we have a multi-step process called triggering, which helps us save interesting events. So we look at the data first in the detector first in a very coarse-grained way, and then we look at detailed information just in little segments, and then we look at the whole detector in order to decide which events we can keep. And lastly, we learned that LHC, in order to process all this data, even this 54 terabytes per day, this cannot be done at any one site. So instead, we use a worldwide computing grid to be able to do this. So this little image was from Google Earth, and it showed us the data transfers between different sites all over the world that are processing LHC data. And so were there any questions from last week that we need to go over? Yes?
Just make sure the grid is all connected with that whole cable.
Yes. So they are, it's generally fiber optic. So the main sites have a dedicated fiber network called the LHC Private Optical Network. And then other sites, so for example, the site that we have here at Chicago uses, typically they use research networks. So it's not dedicated to us, but it's a research network.
Is there any, what happens when one of them goes down?
So we haven't really, so sites go down. It's much more likely that a site goes down, so that there's problems that that particular site either just needs to do software maintenance or whatever. But that's the grid, since it's distributed, that means that data also exists somewhere else. And so we don't get hurt by that. So the downtime for our tier 2, our computing center here is probably a few times a year. It goes down for a day or two. But besides that, then we've got hundreds of sites all over the world, so at any given point, there's over 100 sites up. Yeah?
It's a little unrelated, but I was just curious with Fermi. They never could find the Higgs boson, right?
They did have evidence. Yeah, at the very end. So July, at the same time as the LHC. I don't have a picture. I should have put a picture in the slide from what they observed, but they did.
Did they have difficulty because of their technology, or because the accelerator couldn't get up to the speed of light?
It was because their energy is lower, basically. So it's two things. One, that their energy is lower, and the other, that they didn't have as much data as we have at the LHC.
And how did engineers figure out, I know I'm going off here, but the LHC, they figured out the diameter of the new one. It might be complicated math, but how did they figure that it had to be so many miles in diameter that they would be able to get the Higgs boson as opposed to the Fermi?
Well, that's done by, the diameter is set by the strength of the magnets and the energy that you want to achieve. So that was, they said, we want to build a machine that's 14 TeV. We know we have magnets that go up to 8 Tesla. Then we need this radius.
Okay.
Well, actually what's set, but that's what you would do if you were building an accelerator from scratch. What actually happened is that there was already a tunnel. So it was kind of the inverse, so sorry. So they knew they wanted to get 14 TeV. They had a tunnel that was that big, so they filled it with magnets. Tesla. So,
They had and made it work.
Right, it turns out it's really hard and expensive to bore a tunnel under the ground, as you might imagine. Yeah, at some point for the new machines that they're thinking about building, it's cheaper for the LHC to buy one of those big boring machines that are used for like oil exploration and stuff like that, and then just use it outright than have a company do it for them. All right, so we're going to move on. So what we're going to talk about today is first I'm just going to go over the general strategy for data analysis. What's our framework for how we go about processing events? And essentially, what we always look at are histograms, which is a way of presenting data that is actually very uncommonly seen in the public. So you actually very rarely see histograms. So what we're going to do is we're going to create some histograms here with data from all of you. We're going to be my LHC events, just to get a feel for what histograms mean and how they're useful. And then we'll talk about how we see this Higgs signal emerging from the Haystack, which is basically where we see the Higgs signal in histograms. And then we'll talk about how we know that we really do have Higgs bosons. So there's very strict quantitative rules to determine what a discovery is, and we'll talk about that. All right, so Analysis 101 really does follow the scientific method that you learned probably when you were a kid. So the first step is observation. So we observe the particles at mass. So that leads to questions. And so that would be how do particles get mass? It's kind of what we've been talking about for a while. So we posit that the Higgs field gives mass. This is our hypothesis. And then we must be tested through, so we need to develop a test to test this hypothesis. So we say, then I must observe a Higgs boson, and we say more specifically, I must observe a Higgs boson decaying to 2 Z bosons, so I can see the 2 Z bosons or the 2 photons. The next step is we go and we look for the signal as analyzing the data, and then you draw conclusions, and the conclusion that we've drawn is that the Higgs mechanism is confirmed. And then we go to conferences. Actually, I think, so that's how it works for most analyses. For the Higgs, you have a press conference and have, half the world connected via video when you announce your results. But for everything else that we do, it's pretty much you target conferences and you go to conferences. And then you write papers. All right, so the first step is how do we know what we're looking for? So basically, we need some way for us to decide that what we're seeing in our data is new. So how do we know what new is? So this is a very multi-step process that's called where we use Monte Carlo modeling or Monte Carlo simulation. So there's many ingredients to this. The first is that we start with our theory. So this is our standard model here. You can write the standard model on a coffee cup. It's a pretty elegant thing about it. And then we have all of our possible interactions, of quarks and Higgses and photons and Z bosons. So we start with this. We have equations that we can write down that tell us how particles are produced and when they're produced, what their momentum and their energy are. So we get that from theorists. The next step is we go back to our proton. So let me go back one step. So the thing with this is that it starts with quarks and gluons. That's our initial part, not protons. It's too hard to write down equations for how this proton works. So in order to figure out what we're going to have at the LHC, we take our observations of how quarks and gluons are distributed inside the proton. So as we talked about a few lectures ago, that one quark will take some fraction of the proton's momentum. So we have that. We have those observations from data. And so we add those together. So we know we have a quark with 1/3 of the proton's momentum, one proton's momentum, and another quark, 1/3 of the other proton's momentum. That'll tell us what our sort of initial conditions were for theory. So we take those two, and then we also take our Atlas detector and we simulate it. So we put in a computer program every single piece of material in this detector. That's massive. We take and model every single piece of silicon that's in those inner tracker detectors. We model all of the liquid argon and the lead and the scintillator and the calorimeters. And we model in great detail the magnetic field. So what is the magnetic field throughout this entire thing? So that when we take our computer simulation and we say I made a muon with a momentum of 30 GeV, we know how that muon will deposit energy in our detector. So this is really the backbone of how we understand our data, is by this complex simulation process. And then you see these dice. So what these dice mean is that this theory can tell us how often we'll get a muon produced with 30 GeV, how often we'll get it produced with 25 GeV, how often we'll get it produced with 50 GeV. And what we do is we roll basically weighted dice. So these dice that are weighted such that our simulation will give us muons with 30 GeV at the same fraction that our theory tells us, or 25 or 50. So that way we can build up a set of basically fake events so that we can compare our data to. So that's the general idea about micro simulation. Are there questions on that? Yes?
That's not a proton. It's a bunch of quarks up and down, and their gluons and so on. So why you have all that mess?
Because this is actually what a proton looks like. So a proton has on average 2 up quarks and a down quark. They're bound together by all of these gluons, and there are pairs of quarks and antiquarks that are popping into existence. So it's like this little pair here all the time. So that really is what a proton looks like. And we have detailed measurements of this, how this actually looks in a proton.
So the proton is not made of 2 or 3 quarks and...
Only on average. So that means that's its average content. Yeah, it's a little bit of a weird concept, but that really is what it means. And it is in fact, one of the big uncertainties on how well we can do this whole simulation process is how well we know this, how well we know that the distribution of momenta for quarks and gluons in the proton. For many, not for all measurements, but for many measurements, that's a big, what we call uncertainty. So that's something we don't know very well, so if we don't know the input very well, then we don't necessarily know the output very well. More questions on this? Yeah?
Is a Higgs boson a structure?
Not that we know of. But, yeah. So far, not that we know. We're not able to, that would be very challenging to probe, because usually to understand if you have substructure, you need to have something that exists for a little while, and then you can, so that you can probe its inner structure. It's not actually strictly true, but it's a hard question to answer. We think it's fundamental, though. All right. So this is our basis, and this is what gives us our predictions. And so what we do is we take all this, and we do this millions and millions and millions of times. We roll these weighted dice millions and millions of times. We send it through our detector simulation, and then we send the output of our detector simulation, which looks exactly like the data that we get off the detector, and we send it through that same software chain that we talked about last week. And we analyze it just as if it were data. And so this gives us our baseline for discovery. And so what I want to do now is then so the next thing that we do is we make a bunch of histograms. So I want to go through and talk about histograms and how those work. So this is actually going to be a little bit interactive. I'm going to go through here. We're going to histogram a few pieces of data about our groups. Okay. So let's see. I need to turn this off for a second. So let me pause it. Well, let's see, hold on. If I turn on the black, okay, that's good enough. You guys can see this graph, right? Okay, and you don't need to know the details. So what this graph is right now, which doesn't have any data on it, is the months of the year. So January, 1, February, March, all the way up to December. And this is just a number. And what we're going to do is we're going to histogram your birth months. Okay? So what I'm going to ask is for people to raise their hand, and they're going to tell me what month they were born in. And then we're just going to plot that. We're going to see what the distribution of birth months is for this group. So, 1 second. So, does anybody have a prediction of how this is going to look? If I plot...
It has to be a straight line.
Yes, it should be a straight line. At least with the amount of data that we have here, it's going to be a straight line. So, let's start, and I want to show you how I would fill a histogram if you are all LHC events and your birth month is a piece of data about you. We'll see how we fill one of these histograms. So, raise your hand. Yes?
March.
March. Okay, so what I'm going to do is I'm going to do this red. So it's 3, so I'm going to fill in a little box here.
But don't you need the date?
Oh, I'm just going to do the month.
The month?
Just right now, all I'm looking at is the month.
Okay.
November. All right, so we got another one here.
Why don't you just ask for a show of hands for each month?
I could do a show of hands for each month, but this is, what I'm doing right now is I'm filling a histogram as I would fill data. This is it's a little bit pedagogical, but I think it's instructive. I really think it's instructive.
Okay,
Yeah.
January.
January, okay.
No.
January. Okay, so we get it. So when we have 2 from the same month, we just put another box in that bin. Okay?
November?
Good.
August.
Yes? Wait, you can start calling them out and I'll start writing them.
July.
December.
December?
March.
December.
May.
June.
June.
August.
Yep.
August.
August. Oh my gosh.
December.
Okay.
August.
Okay.
June.
June? I feel like there's some resonance effect going on. January.
February.
February.
September. November.
February. All right, so we just got here. But what I've just done is I've just filled a histogram with your birth months. And so what we're starting to get a sense of is that this is a pretty flat distribution, although not entirely. So this is only a small number of people who shouted out. So if I had everybody's, then I would be able to get a more statistically significant sample. But this is really how we fill a histogram. So we take each event and we figure out whatever the quantity is. So what we've mostly talked about, what we talked about last week, was invariant mass. In that case, I would take my invariant mass, and for each value, I would put one entry, what we call an entry, in that bin. And then by accumulating many, many events, I start to get a sense for what the data is. So we're going to do a few more examples with histograms, but this time I'm not going to draw them up as we go. But we're still going to be interactive, and you're still going to need my data for this. I just have a little computer program that makes it easier for me to put it in and make pretty plots than me drawing on the board. All right, so let's go here. And go here. And go here. All right, so we did. Let me just move this over. All right, so now for this to work, I need people to not be influenced by your neighbors. Okay? So there's 2 things. We're going to histogram 2 more things, but I want you to try as much as possible not to be influenced by what your neighbor said. So the first thing we're going to do, I want you to estimate how many books you read in the past 12 months. Okay? And we're going to plot this. And then we're going to compare to some known distribution, just like we compare to simulation for our data. So, okay, so I'm going to do this a little bit more ordered. I'm just going to start with this section to tell me some, then this one, and then that one, and we'll populate this histogram and then plot it. All right, so roughly how many, yeah, just roughly how many books you think you've read in the last year?
Well, do we have to finish them?
But no, the data that I'm going to compare to, I'm sure people didn't always finish them. So. Okay, so throw them out.
110.
Whoa, whoa. 15. 24.
10.
3.
40.
37.
He said, Joe, we know you.
More?
50.
Yeah, I know. This is going to be very different than our average American, but okay, it's fine. Let's keep on going. It's gonna be
3.
3.
200.
Margaret,
They're romance novels.
6.
Okay.
12.
All right.
2.
30.
20. Any more?
36.
6, 17. Okay, and give me 2 more.
8.
3 or 8? 8. How much more? 1 more? 4. All right. Okay, so let's plot this. So I have a program now. Enter. All right, so this is, oops, sorry, I have to do something first. Okay. So now, this is what I'm doing right now is I'm telling the computer to execute lines. So this is just basically telling it to import all the tools I'm going to use for plotting. And here, I'm telling it that's my data. And here, I'm telling it this is the number of books read per year. So on the x-axis is the number of books read per year, and here is the number of participants. And let me change it. I'm going to change one thing. So right now I've set this so that the number of bins is equal to the total number of books per year, right? So I say I'm treating people who read 5 is 1 bin, 5 books per year is 1 bin, 6 books per year is 1 bin, etc. But I can change that such that there's fewer bins. So I'm going to just do this and just call it 10 bins. Right, so this is a distribution where I've grouped together similar numbers of bins. And in a detector, we would do this, we decide this grouping based off of the resolution of the whatever we're measuring it with. So basically, how well we can measure an energy sets how big our bins are for a detector. So let's say I figure you guys can remember how many books you read to about 15. Doesn't actually make sense clearly for when you're down below 10 books, but good enough for here. So now what I'm going to do is I took the Pew Internet survey of people who read, how many books people read per year. It's going to be here. So I basically, oops, I don't want to do that, but that's fine. Let's do this. So I plotted, ooh, this is coming up, so hold on. I'm sorry, the problem is that it's not rebinning the number of bins here. So this is the data, this is your data here, the number of these little spikes, and the blue is the Pew data, but I want to have the right bin size. So this worked this morning. Last night, let's see, hold on, let me redo this. And then, okay, well, at any rate, what we're seeing here is that except for at the low end, we actually have pretty good agreement in terms of the rates as the Pew data do. So you can see this basically by the fact, this is something that ends up taking some time to learn, but these data points get more frequently spread out, and that corresponds to a lower number of points if we have the whole bin. Just a lot easier to see. Sorry, let me just give it one more try to doing this. Oh, no, okay, it's not going to do it. All right, I would need to write a better program to make it. Oh, no, here it is. Sorry. I got it. Ah, here we go. Okay, so our data is in green. So what we just talked about. And the blue data here is the Pew data. And so what you can kind of see is that we read a little bit more on average, but the general distribution is pretty similar. So if I were looking for neophysics, let's say there's some population of people who can read an insane amount, perhaps only read, that's all they do all day, but maybe we would see a lot of events out here, but we don't. So we have a rather consistent data set. So that's kind of how we do these comparisons. And then there's one more thing that I want us to histogram, because I want to illustrate measurement error, because that's another important concept of this. So I'm going to start again. This time, this is another thing where we have to try to not be influenced by your neighbors. I want you to tell me what's the length in inches from here to the end of that table. Right? So guess how many inches it is from here to this table. And think in your heads right now, take a guess, and then don't hear anybody else's answers and tell me. Right? So we're going to see if you guys are all detectors, what your resolution on length would be. That's our idea, so how well you measure length. All right, so let's start again. Let's start from this side and work our way over. Guesses for how long this is in inches.
144.
144?
Yes.
More.
120.
Any? More.
100.
120.
110.
102.
102, 182, did I hear 182?
110.
152.
130.
104. 85.
90, 96.
120. 125.
112.
108. 82. 72.
120.
75. Both
Yeah, some of the tables.
of them.
108.
Lie down.
90.
Okay, any more?
96.
120. 126.
Okay. All right, so let's plot this. So these are our, oh no, I must have missed the comma somewhere. Hold on. Oh, I see it. Okay. That's the wrong. Yeah. Okay. I need to redo this one. And let me change this to table length. And one more thing. I'm just going to give us. No, that's actually good. All right, so let's look at this distribution. So this is our distribution of length measurements, or guesses. But what we can see is that average here, I would put it somewhere at around 110-ish, right? Would you say that? And then let's say there's a spread here of probably about 15, 1.5 bigs, right? Most of the data is contained within there. Is that fair enough? If we were doing this with a real experiment, we would have a much more quantitative way of determining this, but this is basically our measurement length. And the actual length is 113. So
How much?
it's pretty good.
113.
You know, like we did a pretty good job of getting quite close to the answer. In fact, 113 is the most probable bin, I think, here. So that just gives you an idea of, this is what we try to quantify. We try to quantify when we measure something, how well we do this, and we do this by measuring things that we know really well. So we know the Z boson mass really well. So we measure Z bosons, and then we compare our measurements to what we know the Z boson mass is, 91 GeV, and that tells us how well we measure Z bosons. So that's another aspect of histogramming and where we use it. So there are questions on this part, histogramming. All right. And the thing is, usually what you see when you see data that's presented to the public is they would tell you what the mean of this distribution is, and they tell you the width. But basically what you're always seeing when data is presented to you is data that's been digested to give you the averages or the variance, and so it's not as illustrative as looking at the full distribution. All right. So let's go back to this. All right, so now we're going to look at some histograms of some Higgs data. And what I'm going to do is we're going to look at Higgs decays to Z bosons, and what's going to be plotted is the invariant mass of the two Z bosons. And then we're going to look at Higgs goes to two photons, and what will be plotted is the invariant mass of two photons. And what the ATLAS experiment did was they took and they did basically what we did on the histogram. So they have an animation of, for each run in the LHC, so each data taken period, how many they plotted the invariant mass. And so we'll be able to see the Higgs boson signal actually emerge from this haystack. So I think if I can get my cursor over there. And unfortunately, my new program doesn't do this so well. So what we're seeing here is the data. The black points are our data. It's like the histogram we did there. And the red is our simulation. That's our expectation for simulation. And this is over time. This is from 2011 until through the end of the run. So what you can see here is the data are following the expectations really nicely here. But then if you look here, there's this big excess of data that what we don't have from our expectation. However, when you add in a Higgs signal, that's this part, you see that it matches pretty well. In fact, it matches a little, I mean, there's a little more than what we see. But that's basically how it happens. I'm going to redo it so you guys can watch it again. But this really illustrates both our background predictions. So this is our background for when just there's 2 Z bosons produced without a Higgs. This is another background here, which is when you have a Z boson and some quarks, and those quarks look like another Z boson, and so you get mistaken and you think that you have 2 Z bosons. And then we have our Higgs signal, which is going to come up here. So, does that make sense? Is there any questions about that? Yeah?
What determines those error bars? How does that get decided?
Yeah, so that's a good question. I think in this particular plot, it's just the statistical error. So you know that if you measure only one thing, that it has an error of 1. So you don't know any better. So this is typically the square root of the number of events in that bin. We have additional sources of error, which we'll talk about in a little bit, which are called systematic errors. And that's errors on how well we think we know basically how well we think we know the energy of the invariant mass, so how well we can measure these leptons, which then determines how well we measure this invariant mass. That will also put an error on the number of events that we see in this particular bin. And so in many plots, you'll see that component as well. However, I'm 99% sure that for this plot, all it is that statistical error. And you see that and then, so there's one other thing that you see is that this is a pretty complicated shape, right? I mean, you have this here, which is actually Z bosons. This is a very cool thing where it's a Z boson where the Z boson radiates a photon. Sorry, well, it basically radiates another photon that has the same mass as the Z boson, that has no mass, and then those two muons make the original mass of the original Z boson. So that's a pretty cool little aspect of this. And then you have this, which is what we call continuum ZZ production, which just means that the standard model has some probability to create Z bosons. And so this is why we really need this simulation in order to tell us what the Higgs is. Because if you just saw this, where it's got this weird peak here, and this peak here, and then this other peak here, you wouldn't know what's the new physics or not. And so by having the simulation, we're saying, oh yeah, but the standard model doesn't predict that it predicts only that we have 3 events per bin here, but we're seeing 15 events per bin. Then you know that you're seeing something new. So that is that's the Z boson decay mode. And I want to go next. No, not there. Sorry. Next slide. Okay, so let's see the photon one. So this is the Higgs to 2 photons. So this is plotting the invariant mass of 2 photons. And so automatically what you see here is that there are way more events. So this is in thousands of events versus the Z boson where we only have like 5, 10, or whatever. And then what you're seeing here is here the signal is actually kind of harder to see. So you just see a little bump on top of this very smooth falling line. So this is a case where we do something a little bit different, where what we do is rather than simulating the background, we have the data tell us what the background should look like. So we know from simulation that this is supposed to be a very smooth distribution, meaning that there's no bumps in it, that it's just, I can fit this as a nice falling line. But then when we plot and we look to see, does this data better fit having a bump plus a line, like it has here, and that is our Higgs signal. What's being shown down here is the difference between the blue line and the data points. So let's see. Let's do it again. So we don't see anything, we don't see anything. This also illustrates why we need a lot of data to see the Higgs. Because if we only had enough to produce 500 events, we would never see this. Instead, we start to see this bump arising, and here it is. And so here we can see there's many bins here where you're seeing more events in data than what you expect from the blue line. So that's another way that we look for new physics, is by using the data itself to give us the background prediction, and then seeing how that is different from what we observe. So there are questions on that? Yeah?
I noticed that the background Z jets had a similar
shape
with a peak right around 125 GeV.
Yeah, that's something called sculpting. So the problem is that we have to put cuts on, so minimum bounds on the momentum of the leptons that we can accept in order to see the Higgs. And it just so happens that if you have minimum cuts on the lepton momentum, so like the muon momentum or the electron momentum, that gives you an invariant mass that kind of peaks near the Higgs mass. But we control this by loosening those cuts. So we have a lot of ways that we understand really how much of that component is Z plus jets. And if we see, I think we probably still going here, it's it's less than one event per bin here. So we'd have to get it wrong by a factor of 5 at least for it to be the Higgs signal, which we're going to talk about, because occasionally we do get things wrong. I'll show you an example of that in a minute, not with the Higgs, but it is definitely a concern, and that's something that we try very hard to control. Yeah?
To determine the error, I imagine you have to come up with some sort of expected value. And how do you figure that out and find out whether the actual data you see, how far it is from what you expect from?
So that's partly actually an art of determining what's reasonable. So for many of the errors, it's an error on how well we think we know something, which is actually kind of subjective. But the way that we do this is by looking at things that we know really well, like the Z boson, and seeing how different what we observe is from what we predict. So that's more or less the reason, but it's for each, there's many, so the number of sources of error, okay, so the number of sources of error in this plot are rather small. There's not too many ways that you get 4 muons wrong. But for the photons, there's a lot of things. It's how well do we measure the photon energy, how well does this fit the blue line, how well does that work, how well does that describe the data. There's a huge number of what we call systematic errors that are involved in that measurement, and each one is estimated in a different way. And often it's estimated in multiple different ways to make sure that some similar answer is got on that. All right, so let's go back. All right, so that's how we've seen Higgs, and so the last step is determining at what point, when as you're seeing that data being accumulated, at what point do you say you've seen a Higgs? We saw the progression over time, and as you probably were aware, there were multiple times over the past 2 years where there were Higgs-like announcements, and those different announcements corresponded with different levels of confidence that we had in the fact that we had discovered a Higgs. All right. So basically, what we're doing with statistics is we're saying that if we see something new that we don't see in our simulation, so like that Higgs bump, we need to know how likely it is that it's an improbable occurrence of something we already know, so that it was that Z plus jets instead of the Higgs, or if it was the fact that for some reason, just by a fluke of statistics, we had more of those standard model Z bosons produced than what would typically happen. So that's the basic idea. We need to quantify this. So I'm going to talk about how we quantify this. So we typically quantify this in terms of what's called a normal distribution. So if mu is the number of events that we expected from the standard model at 120 GeV, the number of Higgs to 2 Z bosons, then we can calculate. So we saw that that was about 5, right? I think it was about 5. So then we can calculate out what's the probability it would be that this fluctuated, that this background, it was that instead of measuring 5, that we measured 7, that we measured some other number. So that, because there's just some statistical probability that instead of observing 5, that we'd observe 7. That can happen. You're doing what we call a counting experiment. And so these different things are called confidence levels. So we have a 1 sigma confidence level, which means if we do this experiment 100 times, 70 of the experiments will measure 5 plus or minus, I think, a couple. And then you can do this out. So what's the number such that this fraction of experiments will have a value close to mu? So that's kind of a way of explaining this. And so what we require typically is that it basically has to be above this 3 sigma line. So less than 0.1% of the time when you produce a bunch of Z bosons, there will be more than what we saw in the Higgs signal. So I'm going to give you an example a little bit better of what this means for in terms of events that we have, how rare this 0.1% is, how rare that is. So we're going to talk about snow in unlikely times in Chicago. So a 1 sigma, that 37%, is the number of times that it snows in May. So they've been keeping data since 1885 on how often it snows in Chicago. And 25% of the Mays that we've had since 1885 had some amount of snow. So that gives you an idea of how frequently a background would fluctuate to 1 sigma. So that's, whatever 25 of 129 is. So 2 sigma would be the amount of times it has measurable snow May. So not just like flurries, but we get like half an inch or something like that. So there's been 8 Mays since 1885 where it has snowed. So that's a 2 sigma event. So that's how rare something is. That's how rare a background would have to fluctuate to produce a 2 sigma event. So in that sense, that's rare, but it's not that rare. I think the last time this happened was like in 89 or something like that. So it's not that rare. So clearly, if we're trying to say we found a new particle, this is not, we have to have something that's more stringent than this. So let's talk about a 3 sigma event. So that's an event where it snows in June in Chicago. So this has only happened once in all of the Junes since 1885. And so that's a really improbable event. It's possible. It has happened once. But that's sort of the limit at which we start to say that, hey, maybe this is something new. If we see something this rare. Still don't know that it's actually happened, but it's around that level. So when you first started hearing things about the Higgs boson, which I think was in perhaps December of 2011, I don't actually remember, that was this level. It was like, we think we might see a Higgs boson, and it's about it. If it's not the Higgs boson, then it'd have to be something like snowing in June in Chicago. Pretty rare. But what we say, so the gold standard is what we call the 5 sigma standard. So this is what we say when we've observed a new particle. And that's a 1 in 3.5 million chance. So that's really, really rare. So a few, these are all 1 in a million chances, but a few 1 in a million chances, just to give you some scale. So that's like you tossed a coin 20 times, and every single time it came up tails.
That last one is a lie.
Yeah, so it's funny. I was trying to find 1 in a million chances examples on the web, and the last thing that came up was this link here, which is from a Berkeley statistics course, and so all of them were very California oriented. It was like not so good, but Also, this one I thought was pretty interesting. So that one of the next 25 babies born in the U.S. will become U.S. president. So that will probably happen in just a few minutes. So there's a 1 in a million chance of that one of those babies being president. And then I think what this really says is that there are a ton of people driving in California. That just means that there's a lot of accidents, but there's just, Californians love their cars. So I guess that's what that is. So that gives you a feel for how rare it would have to be that a background faked, what we call faked the Higgs signal. All right, so that's almost true. So what I just told you was almost true. So that's true exact if the data are distributed in this Gaussian, if the probabilities really are distributed like this. So if this 1 sigma thing, 3 sigma really is snowing in June. But it's not actually, and the reason why is because a lot of times what we end up having are measurement errors that mean that there are more events that are populated that's more likely for the background to look very different than what we expected to than what we predict. And that's the reason why we use the 1 in 3.5 million criteria rather than the 1 in 1,000. That seems pretty good, the 1 in June. I mean, that seems pretty good. But this is really why we go to such extremes. It's such a high statistical level is because we do know that we are imperfect, and that occasionally we see 5 sigma effects, what we call effects that are wrong. And I will just give you an example of that in a minute. But before I do that, I wanted to show you how confident we are that the Higgs boson is a Higgs. So this is as a function, this is a complicated plot, but basically all you need to see for this is as a function of the Higgs mass. So if we have 125 GeV Higgs, then the probability that the background fluctuated to give a Higgs disease signal, to give that signal of those 15 events over the 5 events, that probability is basically 10 to the minus 9. So it's a 6 sigma effect. This is, it's 1 in a billion chance that the background fluctuated. And this says, okay, if it were 100, so all the rest of the stuff here is for other Higgs masses where it's very improbable for that Higgs mass to give that sort of value. So don't worry about that. Just worry about this region. What you can see is that it would really be a 6 sigma effect for the background to fluctuate like that. And then for the Higgs situ photons, this one is even stronger. So the Higgs situ photons, that bump on that blue line, for the background to fake that, it's a 7 sigma effect. That is 1 in a trillion probability that it fakes, that the background fakes that. So we're really confident that we've seen a new particle. Really confident. And yeah, so that's that. But I want to show you that the stakes can happen, so that's what I'm going to show next. But are there any questions at this point on this? Yeah?
If you were dealing with data, let's say for Newtonian physics, whether it's gravitation or acceleration, you wouldn't need to use statistics at all because the formulas would predict the data. Is there any possibility that formulas could be developed for the Higgs boson that would predict the data instead of the data verifying the Higgs boson, or is the uncertainty principle kind of rule that out at the subatomic level, operating by equations?
So, yeah, there's a couple answers to that. So one, you would still need to do the statistical procedure even for measurements that are made about things like gravity because there's measurement error that's involved. So measuring something is an inherently statistical property, so you can do it so many times that you're very certain about it, but you typically always have to do some sort of statistical procedure like this. And then for Higgs, it is possible to write down equations for this. That goes back to that first page where or the first one I showed how we do this prediction with the mug that has the snare model on it. The thing that makes it not possible just to write that down for proton-proton collisions is the fact that you don't know, you need to take the distribution of quarks and gluons inside the proton in order to predict it. And you need to take that from data and then you can predict it. However, if we're applying to electrons, which is what's proposed, or electron and a positron, which is proposed for an accelerator in Japan, the International Linear Collider. In that case, there's no substructure to electrons. So to a good approximation, you can write down the equations for what you would expect. In fact, it's something you do, not for Higgs production, but for some similar stuff. It's like a graduate student problem for that.
Okay, thank you.
Yep.
You got the mass down at, but the Higgs is supposed to have zero spin.
Uh-huh.
Has there been any attempts or any experiments for direct measurement?
Yes. Yes. So what you can do, which I'll talk about that maybe a little bit in the last lecture. So you can do, well, I don't know if I'm going to be able to do it, but you can take the Z that takes the case to Z bosons, and you can measure the angles that are associated with that, and that tells you what the Higgs spin was up to a certain amount. So they're fairly confident in spin 0.
At the same level as the mass.
Oh, it's not a 6 sigma level. So I think at that point, so the problem is once you start dividing your data up into each one of the legs and trying to measure angles, yeah, it totally reduces. So it's like I think it's like 3 sigma or something. 2 sigma. So what they do there is also a little bit more complicated. They say they take, okay, does this look like a spin 0 or a spin 1? Does it look like spin 0 or spin 2? So depending upon which question you're asking, the confidence level is bigger. But I can talk about that more in a few weeks. Yeah.
It's quite a convincing case, but are there any prominent naysayers?
To this? No, not to this at this point. I'll show you a case where, in the next slide, I'll show you a case where it wasn't convincing. But this one is pretty convincing. Part of the reason why is because both Atlas and CMS have seen the same level, the same confidence level basically, and it's using different detectors, different data sets. So that's what really makes you sure, and I'll show you that. I'll show this rather famous example. Why don't I show you that one? So mistakes do happen. So this is a plot from the CDF experiment. This happened in 2011, I think early 2011. So what they plotted here, this was the invariant mass of 2 jets. So either a pair of quarks, a pair of gluon, and a quark, in events where you have a W boson. So it's a really weird shape. But what you can see here, sometimes, so you have different background contributions here. This is the case where you have a W produced and just another quark. That will happen. That's the big bulk of this green thing. Then the red here is what happens when you have a W produced and another W, and that W decays to 2 quarks, or you have a W and a Z boson, and the Z boson decays to 2 quarks. And that's that red component here. So what they did is when they took their data points and they subtracted the green, and basically everything but the red from this, so they subtracted the green, the pink, and the blue, what they saw was this. They saw this big peak happening at around 80 GeV, which was this case where you have the W and another W or Z. And then they saw this big excess here. So when they first saw it, they just put the blue line on here to guide your eye. But the red is the prediction. And they saw this big excess, and that looks really significant, right? That looks like something new. And so they checked a bunch of things, and they looked at this, and they said, okay, well, we've got about a 3 sigma excess in the data. We're going to put it out there, and see what other people have to say. They were a little bit on the, depending on which analyzer was giving the presentation about this, how confident he or she was in terms of this is new physics versus this is something we don't quite understand in our data. But basically it was out there for a little while that there was a new particle decaying to 2 jets at around 100, and I think in this case it was like 100, it was above the 125 for the Higgs, when you take into account some corrections that you need for the energy. So this is weird, but this is why I really like having 2 experiments. So this was at the CDF experiment. This result is at the CDF experiment at Fermilab. There's the sister experiment D0, and when they made this plot, they didn't see anything that looked like the signal. So this little histogram is what you would expect if there was new physics here, as the CDF experiment saw, and they don't see anything. They didn't see anything compatible with that. So then that made everybody step back and say, okay, there's something going on here that has to explain the data that's not a new particle. Because if it were a new particle, then D0 would also see it. And what it turned out was they went back, they did a lot more careful checks, and what it turned out was that what they're doing here is subtracting a big background off of this, And if you get the energy of this background wrong by a little bit, it can create a shape that looks like this. And so basically, what they were doing, and it was a little bit more complicated than that because it came down to there are slight differences in the energy of jets if they are from quarks versus if they're from gluons, and they were getting that wrong in their calibrations. And so that's what led to this thing. So occasionally, these things that look very statistically significant are actually just errors in our data. So that's part of why we require 5 sigma, 1 in a million to claim a discovery, and part of why we really like having 2 independent detectors in order to cross-check each other. All right, oops. So this is just the conclusions. New physics is found by comparing data from many events to expectations. We use a lot of histograms. All of our comparisons come from histograms. And a very high bar is set to announce discovery so as not to end up being embarrassed by wrong results. All right, so that's it. Any questions? Yes.
Yeah, so I have a question going back to your elementary school propositions there. And there are actually 2 questions, I think they're related, about how you formulate the problem and the concepts. So if you say that a particle, you observe that a particle has mass, and you ask where does it get it? So let's say a proton, for example.
There's different answers, right? Okay.
So what, the formulating it that way seems to suggest that there is such a thing as a proton that doesn't have mass that gets it from somewhere else.
So I simplified it a little bit. So the actual question that you asked for the Higgs boson is why do W and Z bosons have mass? And there's only one way that they can, I mean, there it's less complicated. In the case of the proton, having mass has to do with the strong force and all sorts of other things like that. So the more precise question is how do the W and Z bosons have mass?
Okay, so the second question I have is, but wait a minute, I think your answer just changes the focus of that first question. It's like, so now you're saying that I should have been more precise and said the W and the Z have mass. So that seems to also suggest that there is such a thing as a W and a Z that doesn't have mass, and it goes and gets it from somewhere. But can I ask the second question?
Yeah.
Because I think it's related. So if the answer has to do with there is such a thing as a Higgs boson, and so my question is, are you saying that the Higgs is mass or it has mass? And then why don't you get the next question, which is, well, if the Higgs has mass, where does the Higgs get mass?
Yeah, so that's, those are all related questions and all questions that sort of get asked in the course of this whole endeavor. So the Higgs boson is actually, we say that the particles get mass actually from the field, and so if they get mass from the field and there should be a Higgs boson, then I should be able to produce a LHC. Just the more, once again, another more precise formulation of why we think we see Higgs bosons if the Higgs mechanism gives mass to particles. And then the next question is how does the Higgs boson get its mass? So there's many ways that we can attack that problem. So one, we have theory tells us basically theory has hypotheses about how Higgs boson gets mass, and then we can go test them because it'll mean if the Higgs boson gets its mass in this particular way, then we should see new particles in. So one of the problems with the Higgs mass is its actual value is kind of strange. So the 125 GeV, that's a little bit of a strange mass. So it does suggest that there could be new particles, which basically could say that we need a whole host of new particles called supersymmetry, which would make the Higgs mass its value. And so we're looking for supersymmetry. So if we do observe supersymmetric particles, then that'll tell us something about the Higgs mass. And I'll talk more about this specifically in 2 weeks when I talk about what's next for the LHC. So basically, what are the implications of the fact that we've seen a Higgs boson with a mass of 125 GeV, and also what other things we're looking for.
Does this lead to an unending series of questions about where does the previous mass come from?
Yeah, but then, yeah, it does. But that ends up getting into, I mean, some people will probably be happy at some point with an answer and just say this is what it is, but it's all, I mean, it's all about how you understand the way the universe works, and it's always asking more questions. Also keeps us employed as long as the government will fund it.
Yeah, I am wondering why or how the Higgs field and the Higgs boson give mass to energy. When you have energy between particles, and that is translated into mass.
So that energy and mass, that energy mass equivalence is something that comes out of the relativity, special relativity. And so I'm trying to think of the right way to phrase this. So we know, so basically we know from relativity that energy is equivalent to mass and vice versa, and we know from particle physics that mass comes from the Higgs boson. And mixing those two, so actually particle physics is totally coherent and totally works with special relativity. Those two work together, but then when you do talk about general relativity, which is the more broad definition of energy and mass equivalence, in that case, then it gets a lot more complicated. So then that becomes a lot harder for me to answer your question. In fact, I just went to a program this week about it. It's a very active field of research. But yeah, so I don't really know exactly how to answer your question. I mean, it's just that we know from one thing that, and we know observationally that mass and energy are equivalent, and then the Higgs gives mass to particles, and it just so, okay, there's also another component that it just so happens that the mass that we have from the Higgs is the same as the mass that we have from gravity, or it's the same value, but let's not, yeah, sorry. It's not a very coherent answer, but the point is that intersection between the energy mass equivalence, which is special relativity based, and the particle description is, they're complete, as far as we know, completely compatible, but it's hard to talk from one to the next.
So it will be a time that it will be able to be more coherent or more...
So people hope so. So string theory is one way of doing that. The problem is that when you start talking about gravity, the scales that you have to talk about are very different. So it's either very, very small distance scales, much, much smaller, or very, very large masses, much, much larger than anything we do in accelerators. So as far as our intents and purposes at the LHC, there's no such thing as gravity, and we don't really deal with it. There are experiments. There's one experiment actually going on at Fermilab, which is what I heard to talk about this week, where they're looking for basically evidence that space-time, more or less, has this quantum nature. So this is also partially like a problem of quantum mechanics versus general relativity. So they're looking for this as well. So there are experiments that could tell us, could give insight into the fact that you can really use the same description for both general relativity and mass. But it's mind-bending. It's very mind-bending.
Thank you.
Yeah?
Yeah, now, on your graph with the photon-photon decay, it looked like there was only something like 100 or 150 events comprising that bump, compared to 2,500 events. That's something like 5%.
Yeah.
So that's really about what we're talking about here.
But that's it.
There were no bumps as you got further up in energy that were discovered.
Correct. We've been looking, but there's nothing else so far. No other ones.
if there were these 3 other Higgs that are possibly predicted by other theoreticians, other than the bare bones Higgs that says there's 1 Higgs, would you have expected them to show up on that graph?
So it depends. It depends a lot about what the structure of the theory is that produces those extra Higgs. So in short, because we haven't seen them doesn't mean that they're not possible. So in some cases you can look for them, they decay to Higgses. So there are some searches that are looking for the invariant mass of 2 Higgs. So first you have to see 2 Higgs particles in one event, which is very rare. But then taking the invariant mass of those, and that might be evidence for a new type of Higgs boson. Or you can have one of these new Higgses decay to a Higgs and another particle, like just a B quark. It's something, if the Higgs has charge, then it can decay to a neutral Higgs and a B quark. And in that case, so basically these are all much rarer than the lowest mass Higgs. And so we expect we need a lot more data to see them.
If they're that much rarer, then you wouldn't even see a bump. It might just be like 5 extra events.
Right now, yes.
1,000 events.
That's why we're going to run the LHC for a lot longer. And so basically the statistical precision on that will increase as we have more data. So that we just need more data to answer some of those questions.
With a totally different concept of nuclear energy and power plants, is there any way, I know these are very small amounts of energy, but they're very small particles too. Is there any way that this can lead to some sort of renewable energy?
Not that I know of.
I mean, you have to have a lot more events, to say the least. You get photons and that's it, but I'm just wondering if there's a way to solve the energy crisis using this as opposed to nuclear energy.
So, I'm going to give you 2 answers on that. One is a total punt, where I say, okay, every time we've discovered new particles and phenomena, it's been completely opaque, and we've never been able to see how you would ever possibly use it in anything. I mean, not in my wildest dreams can I tell you a way to use Higgs bosons. Right. But the same was true when they discovered electricity. They thought it was just a weird thing, and now it powers all of our devices.
It's just when you're playing with mass to energy, energy to mass, we're opening up a whole other area that, like you said, who knows what can be there.
Yeah, I mean, I don't want to, I feel like how this gets used is really a limit of creativity on our part right now. But there is something that's pretty interesting that is related to using to make nuclear energy a lot safer.
No.
So what you can do is, so the problem with nuclear reactors is that how fast reactions happen is driven by basically how much fissionable material you have in your reactor. And all the times that we've seen nuclear disasters, there's been some problem where there's been the fissionable material has been stuck in the reactor, right? It's like you've got the rod stuck in the reactor and then the whole thing melts down. So that's because there's basically these mechanical and electrical problems that prevent you from stopping the chain reaction. But there is really cool research being done where you take an accelerator, like a Fermilab, and you catalyze the nuclear reaction with a beam of particles. So there's certain nuclear fissions that only happen when you've got a beam of particles incident on them. And so as soon as you turn that beam of particles off, the nuclear reaction stops. So this is one of the, there it's very safe. So there's no way you're going to get a beam of particles stuck in the on position. It's hard to get a beam of particles in the first place. So there's no way you're going to be able to make that just a continuous reaction. So this is something that Fermilab has been thinking about for a long time, and they're kind of working on this. And India is very interested in this as a renewable energy source, or not renewable necessarily, but as a low carbon emission energy source. So there is some connection with particle physics and renewable energy. It's just not quite what you're thinking about.
Generally, governments are willing to spend billions of dollars for science when they get a bomb or energy.
Yeah, so that's part,
Scientists are excited about the particles, but they're more interested.
We're also interested about having safe nuclear energy.
Sure.
I mean, that would be amazing, because if it would be safe, it's got no carbon emission, and so that's wonderful. It's just hard to make it safe.
If it did get stuck,
and it's hard to keep the residual radioactive,
You're the waste problem. But
Yeah.
the waste, yeah. the-
and then mining the uranium and leaving the shit all over the place, and
Yeah,
you
there's
know.
a lot, let's put it this way, there are a lot of technical problems to be solved
Yeah.
with it. It's the way most physicists see it. I don't want to speak for everybody, but it's really the way I see it, is that as it is right now, there's still a lot of problems with it. And part of it is things like safety in terms of reactions, and another part was dealing with the waste, and the way we deal with it isn't very good right now. So but it's not fundamentally, I think fundamentally it's an excellent power source.
If it did get stuck on, you could always hit it with a 5-pound sledge.
Yeah, exactly. Then you're done.
You said that.
All right.